Black holes are among the most fascinating objects in the universe. Imagine a place where gravity is so strong that nothing, not even light, can escape. This is a black hole, a region of space-time where the pull of gravity is inescapable. Black holes form when massive stars collapse at the end of their lives. They are cosmic remnants, incredibly dense objects with gravitational pulls so strong they warp the fabric of space-time itself. For decades, scientists believed that at the heart of every black hole lay a singularity. This singularity is a point of infinite density, where the laws of physics break down. It represents a point where our current understanding of physics collapses. It's a place where space and time as we know them cease to exist. The singularity concept has always been a source of intense debate and mystery. However, recent breakthroughs in black hole theory are challenging this traditional understanding. New models suggest a different picture, one where black holes might not be the cosmic dead ends we once thought. These discoveries could revolutionize our understanding of these celestial objects and their role in the universe. The singularity, a point of infinite density at the heart of a black hole, has long puzzled physicists. This concept arises from Einstein's theory of general relativity. However, it also leads to contradictions with other fundamental laws of physics, particularly quantum mechanics. New theoretical models are emerging that propose the existence of singularity-free black holes. These models suggest that instead of a singularity, black holes might have a core of highly warped space-time, but with a finite density. These regular black holes offer a way to reconcile the intense gravity of black holes with the principles of quantum mechanics. One promising approach is loop quantum gravity, which suggests that space-time is quantized, meaning it exists in discrete units rather than a smooth continuum. Applying this theory to black holes suggests a bounce mechanism. Instead of collapsing into an infinitely dense point, the collapsing matter reaches a critical density and rebounds outward, forming a highly compressed but finite core. The idea of black holes as cosmic portals, connecting different parts of our universe or even different universes altogether, has long captivated the imaginations of scientists and science fiction enthusiasts alike. While still highly speculative, recent theoretical work suggests that this might not be pure fantasy. The traditional picture of a black hole ends at the singularity, a point of no return. However, some physicists propose that instead of annihilation, matter and energy falling into a black hole might encounter a white hole on the other side. A white hole is a hypothetical region of space-time where nothing can enter, only exit. This concept emerges from the mathematics of Einstein's equations, though their physical existence remains unproven. If black holes do connect to white holes, they could act as cosmic tunnels, transporting matter and energy across vast distances or even into other universes. This concept, often referred to as wormholes, is a staple of science fiction, offering shortcuts through the vast expanse of space-time. Section 4. Echoes from the Abyss, Observational Evidence. While the extreme conditions within black holes make direct observation impossible with current technology, scientists are finding intriguing clues in the universe around them. These observations provide indirect evidence that supports the theories of singularity-free black holes and even their potential as cosmic portals. One such piece of evidence comes from the detection of high-energy neutrinos originating from distant galaxies. Neutrinos are almost massless, ghost-like particles that rarely interact with matter. Their detection suggests powerful cosmic events, potentially linked to black holes. Telescope observations, particularly from the James Webb Space Telescope, are also shedding light on the nature of black holes. The JWST's ability to observe in infrared light allows it to peer through dust clouds and see objects in the early universe with unprecedented clarity. These observations are providing valuable insights into the formation and evolution of black holes, potentially revealing clues about their true nature. Section 5. The Galactic Ballet, Cosmic Rotation and its Implications. Observations of galaxies across the universe reveal a curious pattern. A significant number of them rotate in a surprisingly uniform direction. This galactic rotation bias presents a puzzle for our current understanding of cosmology, as it suggests some underlying influence affecting the formation and evolution of galaxies over vast distances. One intriguing explanation for this observed bias involves the concept of our universe existing inside a rotating black hole. This mind-boggling idea suggests that our universe, vast as it is, might be contained within a larger parent universe. The rotation of this parent black hole could then impart a subtle spin to the matter within it, influencing the direction of galactic rotation. While this theory is still highly speculative, it highlights the profound implications of black hole research. Understanding these cosmic giants might hold the key to unlocking the secrets of our universe's origin and its place in a potentially much larger multiverse.